Hello, grade 9. We will discuss here quadratic inequality. So, a quadratic inequality is an inequality of second degree polynomial in the form ax squared plus bx plus c is greater than 0. So, this symbol here is a symbol of inequality. Ax squared plus bx plus c is greater than or equal to 0. This one. Or ax squared plus bx plus c is less than 0, this one, and ax squared plus bx plus c is less than or equal to 0. So these are the forms of quadratic inequality. Notice that on the left side, it's an expression of a quadratic expression, and on the right side, it's 0. So we have to uh, transform quadratic inequalities in this form so that we can apply the methods of solving uh, the roots of quadratic equations in the future. Now here are examples of quadratic inequalities. X squared minus 6x minus 16 is less than or equal to 0. So the bar below the symbol less than is read as equal to. We also have 2x squared minus 11x plus 12 is greater than or equal to 0. Or x squared plus 4 is greater than 0. Or we also have x squared minus 3x plus 2 is less than or equal to 0. So notice that the left side of this inequality are quadratic expressions. So we have the quadratic term here, the linear term, and the constant term. And on the right side, it's always, as much as possible, it should always be equal to 0. So that in the future, we can solve the boundaries that will determine the intervals of the solution set using quadratic equation and the roots of quadratic equation. So note that solving a quadratic inequality or quadratic inequality in algebra is similar to solving a quadratic equation. So we use the four methods in solving quadratic equation. So we may use any method, but it's just a matter of using the most convenient way. So we can use factoring, we can use quadratic formula, we can use completing the square or extracting the square root to determine the boundaries. Okay, for example, find the solution set of x squared minus 8x plus 12 is greater than 0. So we have to transform or use the corresponding quadratic equation of this inequality first. So we have x squared minus 8x plus 12 is equal to 0. So for the meantime, we have to use equal to instead of greater than. Then from this quadratic equation, we may find the roots by factoring. So factor x squared, we have x and factor 12. So we have to think of the factors of 12 such that if we add those two factors, we have negative 8 as the sum. So we have 6. We have 6 here, and or negative 6 and negative 2. So if we multiply negative 6 and negative 2, the result is positive 12. And if we add negative 6 plus negative 2, the result is negative 8. Then, equating each factor to 0 by using zero product property. So, x first is equal to negative, or x minus 6 is equal to 0, or x is equal to 6. And x minus 2 is equal to 0. So, x is equal to 2 now. Now, from these roots of the quadratic equation, we have to identify which regions will satisfy, which region in the number line will satisfy our inequality. Here, using the boundaries, which are the roots of the corresponding quadratic equation. So, one boundary is 6, so we may label one part here as 6, then the other is 2. Of course, 2 should be put at the left of 6 because 2 is less than 6. Now, there are 3 regions to be considered here, or the numbers which are found at the left of the first boundary, which is 2, the region which is found between these two boundaries from 2 to 6, and the region which is found at the right of the upper boundary, which is 6. Now let's try, or we have to test each boundary if which one will satisfy our inequality. So let's try a number which is found at the left of 2 here in this region. So a number which can be found at the left of 2 is, say, there is 1 here, and there is also a 0 here. So I think the easiest, or the number that we could use most conveniently, is 0. So we may use x equals 0. So substitute it to the original inequality here. We have x squared, but x is 0, so 0 squared, minus 8x, so 8 times 0, plus 12 is greater than 0. 0 squared is 0, so we may cancel this out now. Also, 8 times 0 is 0, so we have 12 is greater than 0. So this is true. That's why one solution set is found in this region, which is from 2, but 2 is not part because we don't have an equal sign here. From 2, then going to the left. So from here, 2, then going to the left. So this is one of the solution sets. Then another, we may test the region between the two boundaries, between 2 and 6. So let's try a number which is found between 2 and 6. Let's try, say, there is a 3 here, there is 4, and there is 5. So let's try 3. X is equal to 3. Substitute again 3 to the original inequality. So you have 3 squared minus 8 times 3 plus 12 is greater than 0. But 3 squared is 9, minus 8 times 3 is 24, plus 12 is greater than 0. So simplifying this operation, 9 minus 24 is negative 15, plus 12 is negative 3. Negative 3 is greater than 0. So it's not. It's a false. So we cannot use the numbers between 2 and 6 as our solution set. Now let's try the numbers which is found at the right of the greater boundary from 6 and to the right. So if we pick a number which is at the right of 6, we can use 7, we can use 8, we can use 9, we can use 10, or any number which is found at the right of 6. So we may use 7. So let's just try to test uh, x equals 7. So from our original inequality again, 7 squared, because it's x squared, minus 8x, so 8 times 7 plus 12 is greater than 0. But okay, so we may continue it here. 7 squared is 49, minus 8 times 7 is 56, plus 12 is greater than 0. But 49 minus 56 is negative 7, plus 12 is positive 5. So 5 is greater than 0, which is true. So we have a true here, we have false in the middle, and we have also a true on the left of 2. Now, we may describe the solution set to solve or to find the solution set of this. So we have x in set notation, x such that how are we going to describe the numbers at the left of 2? So they are the numbers which are less than 2. So x is less than 2, which is the first boundary, or another boundary or another set is found at the right of 6 here. So how are we going to describe them? It will be x is greater than 6. So that is how we set the solution set of this uh, quadratic inequality. So this is the answer. Another example, find the solution set of 2x squared minus 5x is less than or equal to 3. So we have to arrange this first into a form of a quadratic equation. So 2x squared minus 5x, 3 here is under at the right side, so we have to transpose it to the left side. It will become negative 3 now, is equal to 0. And let's try to do factoring here to find the roots. So 2x squared, if we factor it, since it's a prime, so 2x and x, and 3, if we will factor it, let's try 3 here, negative, and 1 here, which is positive. So that if we multiply 2x times negative 3, that's negative 6x, and 1 times x, that's 5x. And if we try to add them, if we are going to add them, the result is negative 5x, which is the linear term in our corresponding quadratic equation. So our factoring is correct. Now let's use 2x plus 1, the first factor, to solve for x. Equate it to 0. So 2x plus 1 equals 0. Transpose 1 to the right side of the equation. So we have 2x equals negative 1. Divide all by 2. So x equals negative 1 half. And the other factor, so we use it also to find the root, the remaining roots. So x minus 3 is equal to 0. And transpose 3 again to the other side to solve for x. So we have x is equal to 3. Okay, so these are our boundaries. We have x is equal to negative 1 half and x is equal to 3. So on our number line, we have uh, negative 1 half. We have to use it here or label it here as negative 1 half and positive 3. Now, we use the numbers at the left side of the negative 1 half to test if which will satisfy our inequality. So the numbers which can be found at the left of negative 1 half could be negative 1, negative 2, negative 3, and so on. So for convenience, we may test or we may use negative 1 as part of the solution set. So x equals negative 1. Let's substitute negative 1 to our original inequality. So we have 2 times negative 1 squared minus 5 times negative 1 is less than or equal to 3. So 2 times negative 1 is squared. But negative 1 is squared is as good as positive 1. So that's 2. And negative 5 here times negative 1 is positive 5. Positive 5 less than or equal to 3. But 2 plus 7 or 2 plus 5 is 7. 7 is less than or equal to 3. So this is false because 7 is never less than 3. So we cannot have our solution set in this part of the number line. Now let's try the region or the part which is found between the two boundaries from negative 1 half to 3. So let's pick a number which is found in this part. So in this part there is 0, there is 1, and 2, and of course 3. So let's test the inequality using 0. So test x equals 0. By substituting 0 to the original equation again, we have, or inequality I should say, 2 times 0 squared minus 5 times 0 is less than or equal to 3. But 0 squared is 0. And number multiplied by 0 is still 0. So this is as good as 0. And negative 5 times 0 also is 0. So we have 0 plus 0 or 0 minus 0 is still 0. So 0 less than or equal to 3. 0 is less than or equal to 3 is true. So we have found part of our solution set. So it is here on this part, the region between negative 1 half, and positive 3. Okay, so let's try another part. The region which is found at the right of our upper boundary, which is 3. So let's identify a number at the right. So let's say 4 or 5 or 6. So we may use x is equal to 4. So substituting 4 to our original inequality, we have 2x squared, but x is 4. So 4 squared minus 5x, but x is 4, is less than or equal to 3. But 4 squared is 16, and 2 times 16, in this part, 2 times 16 is 32, and minus 5 times 4 is 20, less than or equal to 3. But 32 minus 20 is 12. So 12 is less than or equal to 3, and that is, again, that's false. So a solution of this inequality cannot be here. So there's only one region which satisfies our inequality, and it is between negative 1 half here and positive 3. So therefore, our solution set should be x such that. So we have to describe the numbers between negative 1 half and 3. So these numbers are called x. So x such that 1 half is less than, and 1 half is part of the solution set. Now, so we have to put an equal sign below the symbol less than. Negative 1 half is less than x, but x is also described as less than 3. So x is less than or equal to 3. So this is our answer. Here's our next example. Find the solution set of 2x squared plus 5x is greater than or equal to 12. So again, we have to transform the inequality first into its corresponding equations. So we have 2x squared plus 5x is equal to 12. But the right side of the equation should be 0. So we have again to transpose 12 to the left side. So we have 2x squared plus 5x minus 12 is equal to 0. Then let's try factoring to find the roots of this quadratic equation. So factoring 2x squared will give us 2x times x, and factoring negative 12 will give us 4 times 3. Let's try 4 and 3 for the meantime. So the product of the factors of 2x squared and factors of negative 12 should give us the linear term 5x. So let's try. Since negative 12, or since 12 is negative, let's try negative 4 here and positive 3. So that's negative 4 times positive 3. That's negative 12. And let's try to multiply the outer terms, the inner terms. So the result should be positive 5x if we add. But 2x times negative 4x is that's negative 8x x, and 3 times x is 3x, and if we add them, then that would be negative 5x. So it's not positive 5x. Our linear term in our original quadratic inequality is positive 5x. It's here, positive 5x. So our trial is not correct. So we have to change the signs of the factors of 12. Let's try positive here and negative here, so that 2x times 4 will give us positive 4x, or positive 8x I should say, and 3 times negative x will give us negative 3x, and if we add, it will give us positive 5x, which is now the sign of our linear term in our quadratic equation. So therefore, our factoring now is correct. We can identify the roots now, which is the first one, 2x minus 3. The first factor is equal to 0. And transposing 3 to the other side, we have 2x is equal to 3. And dividing all by 2, we get x here is equal to 3 halves. And the other factor, we have x plus 4 is equal to 0. Again, transposing 4 to the other side, we have x equals negative 4. So the boundaries are 3 halves and negative 4. So in a number line, assigning this or labeling a part of our number line based on our boundaries, the first boundary is negative 4. Of course, negative 4 is at the left of positive 3 halves, because negative number is always less than the positive number. Okay. Now there are 3 regions to be considered again. At the region which is found at the left of the first boundary here, negative 4. The region which is found between the two boundaries here, between negative 4 and positive 3 halves, and the region which is found at the right of 3 halves. Now let's test if which region satisfies our inequality. Okay, let's test a number which is found at the left of negative 4. Let's try negative 5 here. So negative 5, so we have 2 times negative 5 squared plus 5x. So 5 times 5 is greater than or equal to 12. But negative 5 squared is 25, and 25 times 2 here is 50. So we have 50 plus 25 is greater than or equal to 12. But 50 plus 25 is 75. And 75 is greater than or equal to 12. So since 75 is greater than or equal to 12 is true, then one solution or one part of our solution set is found in this region, the region which is at the left of our first boundary, negative 4. Next, let's try, we have to clear up this space. Okay, let's try another region, which is at the middle of -4 and +3 halves. So between -4 and +3 halves, there's -3, -2, -1, 0. There's 0 here. And this 3 halves is 1.5 or 1 and 1 half. So of course, there's also 1 here. So there's -3 here, -2, -1, 0. Now, we may use 0. So let's just use 0 for convenience as our test point. So let's say x, or let's use x equals 0. Substituting 0 to our original inequality, we have 2 times 0 squared plus 5x. So plus 5 times 0 is greater than or equal to 12. But 2 times 0, or 0 squared is still 0 times 2, 0. 5 times 0 is 0. So 0 plus 0 is still 0. 0 is greater than or equal to 12. From this statement, 0 is greater than or equal to 12 is false. Okay? So here is true. This region is false. Now let's try the third region, which is the numbers at the right of our upper boundary, which is 3 halves, from here to the right. So let's pick a number which is found at the right of 3 halves. Let's say 2. Because 3 halves again is 1.5, so at its right is 2. So let's test 2. Test x is equal to 2. By substitution, so 2 times 2 squared plus 5x, but x is 2, is greater than or equal to 12. 2 squared is 4. This is 4 here. And 2 times 4 is 8. So that's 8. Plus 5 squared is 10. Is greater than or equal to 12. But 8 plus 10, we may continue, is 18. And 18 is greater than or equal to 12. Is 18 greater than or equal to 12? That's true. So this region here, since 18 is greater than or equal to 12, is true. So this region will satisfy our inequality. Therefore, to express our solution set, let's have x such that, how are we going to describe again the numbers at the left of 4? And 4 is part of this solution set. So the numbers at the left of -4 is x such that x is less than, or since 4 is part of the solution because of this symbol here, equal to, so, or -4, I should say, -4 is part of the solution because of this symbol here. So x is less than or equal to -4. -4. And also, the numbers at the right of the upper boundary, including the upper boundary, which is 3 halves, can be described as x is greater than or equal to +3 halves. So this is the answer. I read it again. The set of x such that x is less than or equal to -4 or x is greater than or equal to 3/2 as being shown in this number line here. Now here are your exercises. You can pause this video so that you can focus on answering these questions on quadratic inequalities. There is an answers key at the end of this video, so you can refer to the answers key so that you can check if your answers here are correct. So thank you for watching.